Hello students, welcome to today's lecture. Today we're going to discuss liquid filtration. Okay, you already know what do you mean by filtration, right? So filtration means like separation of solid particles from liquid, right? We all have filters in our home which provides you pure water by separating microbes, dust particles from the tap water, right? So that we can drink pure water, right? So we all have filters at our home. So the same process we're going to discuss, but in a scientific manner. So we will understand how to, you know, uh, what are the principles behind filtration, okay, and what are the modes available for filtration and so on. Okay, so if you want to read the definition of filtration, so this separation of solids from suspension in a liquid by means of porous medium or screen which retains the solids and allows the liquid to pass is termed filtration. So what do you mean by suspension? So if you have a liquid and we have particles suspended, so this is nothing but suspension. Okay. So you want to filter and you want to separate the liquid and the solid particles, right? So on the bottom you have pure liquid, at the top you have solid particles collected. So how to separate this solid particles? So using a porous medium in the sense it has some pores. So if you have cloth, so you have pores, right? Or screen, as you already discussed, so it can retain the solids at the top. So the solid particles will not be allowed to pass through the pores. So you have to choose the porous medium such that you prevent the uh, particles from passing through the pore. Okay, so this is filtration. So what are the main factors to consider when you want to select the equipment, okay, and operating conditions? So you want to select equipment for filtration, okay, and the operating conditions. What are those? So these are the main factors you have to keep in mind while selecting particular equipment and the operating conditions in which you are going to perform the filtration process on that equipment. Okay. So first one, the properties of the fluid, particularly its viscosity, density, and corrosive property. So you have to choose the fluid based on its viscosity, density, and corrosive properties. Suppose it is very acidic. You want to filter the acidic suspension, so it is difficult, right? So if you have very high density fluid, then it's also be a difficult. If it has very high viscosity, then the filtration will be also difficult. The nature of solid. So the solid particles in the suspension, what is the particle size, what is the shape, what is the size distribution, packing characteristics, so on. See the concentration of solids in suspension. If you have large concentration of solids in the suspension, then it will be very difficult, right? The particles will block the filter medium. So you have to take care of that also. The quantity of material to be handled and its value. So how much material you want to produce per hour or per day, and what is the value of it. If it is a gold, then definitely it is a very high value, right? So you have, it is very sensitive. So we have to select very, good equipment. Whether the valuable product is solid, fluid, or both. So sometimes the valuable product may be some kind of solution here, or purely the solid. If you have solid, you can collect from the top. If it is fluid, then you have to collect from the bottom, or both are important. This can be important also, this can be also important. whether it is necessary to wash the filtered solid. So these are the solids, right? Now these solids will be there along with some other dust particles or some waste material. So you have to wash it. Whether very slight combination caused by contact system filter with the various components equipment is detrimental to the product. Sometimes these solids, if it react, the solid can react with the water, liquid, or it can react with the filter medium and so on. So it is also important to consider. Whether the feed liquor may be heated. Suppose the feed you are trying to filter is heated. It is at like 60 degrees Celsius or maybe like boiling 100 degrees Celsius. So if you pass this hot material on the filter, then filter will get heated. It will melt. It can melt, right? So these things also you have to consider. Whether any form of pre-treatment might be helpful. Okay, sometimes you can pre-treat the feed so that you can get better product, or you can do the filtration easily, right? So suppose you want to filter the drain water, then it's very difficult, right? So first you remove the larger solid particles like plastic, then only you can filter it, right? So this kind of pre-treatment is necessary sometimes. Okay, this is a general schematic diagram of a filtration. Okay, so first you have slurry. Okay, so this part is slurry. This is the side view, and top view can be rectangular cross section or circular. It depends. So you have the slurry. Slurry means you have liquid and you have suspended particles, solid particles, right? So definitely at the top, the pure liquid will float. Okay, the solids will settle at the bottom. So this is slurry. And this is your filter medium. Filter medium can be cloth or some kind of filter paper or ceramic filters, anything. So this is your filter medium, like cloth or this. Okay, so and the filter medium, you have to give some mechanical support, otherwise it will just fall down, right? So you have to give some mechanical support. So you have support for filter medium. Now, what is filter cake? So at first, at the start of the filtration, there will be no filter cake. So there will be only slurry and your filter medium. So the liquid will pass through this, right? So that is called filtrate. So liquid will pass through it and the solids will get collected over the filter medium, right? And over time, what will happen? The solid particles will get accumulate here, layer by layer, right? And they will form a kind of cake here. So this is called filter cake. And again, this will offer some resistance to the flow. So as this solids particle gets deposited over the filter medium, then what will happen? The filtrate flow rate will start to reduce. Okay, that's why at the start the filtrate flow rate will be, let's say in meter cube, it will be high at the start when there will be no filter cake form. As the time passes, then what will happen is there will be filter cake here. It will offer resistance to flow. Then the filtrate flow rate will reduce. Okay. So this is the principle. So within this, the important factors on which the rate of filtration then depends. So let's assume that the filtrate is very important product. So I want to know the flow rate of this filtrate, and on what factors this flow rate of the filtrate will depend, or rate of filtration. So nothing, the volume of filtrate collected per unit time is nothing but rate of filtration. Okay, so on which factor it depends. Okay, so the thing is the drop in pressure from the feed to the far side of the filter medium. So what is the pressure drop between this point and this point? So what is the pressure drop? So based on this pressure drop, the rate of filtration will depend. How? So if you, so at the start, at time equal to 0, you know there is no filter cake, right? So the rate of filtration is already high, right? But as the time progresses, what will happen is the rate of filtration decreases because of the resistance offered by the filter cake, right? Okay. So if you want to maintain the constant flow rate throughout the process, then you have to increase the pressure with time, right? So at start, let's say you have applied 10 atmosphere, right? So the flow rate will be something, okay? Then the cake will start to form here. So you have to increase pressure to maintain the same flow rate as previous, okay? The area of the filtering surface. So if you see the top view, so what is the area of this filter medium? What is the surface area of this? So the more is the surface area, higher will be the filtration rate, right? The viscosity of the filtrate, what is the viscosity of this? If it is a high viscosity, it will be less, right? The flow rate will be less because of the resistance due to viscosity. The resistance of the filter cake, what will be the resistance of this solids deposited here? Suppose the solid particles deposited are very, lightly packed, then the flow rate will not be much affected. But if it is densely packed and there is no pores in between them for the liquid to pass, then if there are no pores, then definitely the flow rate of the filtrate will decrease, right? Or there will be no filtrate. Okay, so that is also important. That is the resistance offered with a filter cake, this one. The resistance of the filter medium and initial layers of the cake. So resistance of the filter medium. The filter medium you have used. If you use large pores medium, let's say you have large pore, then the filtrate will be high, right? Everything will pass. But if you have very small pore, then the resistance of the filter medium will be high. Okay. So we have two types of filtration processes. Okay. One is cake filtration. Another is deep bed filtration. So what is cake filtration? As you can see here, it is same. So cake filtration, in cake filtration, what happens is the filter cake forms. Okay. And in deep bed filtration or depth filtration, what happens is you have filter medium and the particles go inside the pores of the filter medium. So they will offer some kind of resistance. So this kind of filtration will be deep bed filtrations. Okay. So if the pores is large enough, then the filtration will not be much affected. If the pores are so small that the particles are clogged between the pores, then definitely it will affect. Okay. So typical examples are air water filtration. And sometimes you want to wash the solids, right? So you can clean by back flushing. Okay. Sorry, back flushing means suppose the pores are clogged with this solid particles, then you have to remove it, right? So you can apply some pressure from this bottom so that it can go out. Okay, that is also called back flushing. And so we have two types of filtration. One is cake filtration, another is deep or depth bed filtration. Okay. And within these two types, we have modes of filtration. What are the two modes? Modes are dead end filtration and cross flow filtration. So if this is the filter medium, so this is the pores of the filter medium. So if you apply pressure drop in this direction, then it is called dead end filtration. If you or if the flow is happening in this direction, that is also dead end filtration. If this is your filter medium and fluid is flowing or suspension is flowing in this direction, so you can see this is area normal and the flow direction is this perpendicular direction. So if it is parallel, this is dead end filtration. If it is perpendicular, this is called cross flow filtration. So the fluid is flowing across the filter medium, okay, not through the filter medium. So if it flows across the filter medium, then it is cross flow filtration. Okay. In this chapter, we'll mainly discuss cake filtration. Okay. So it is mainly cake filtration, not depth or deep bed filtration. So we'll mainly focus on cake filtration. So what is the filtration theory? Okay. So you can see this equation. So according to filtration theory, what is UC? UC is the superficial velocity of the filtrate. Okay, what do you mean by superficial velocity? So if the fluid is freely flowing, then it is velocity of the fluid, right? But if this same fluid is flowing through the solid particles, so you have suspension of solid particles and fluid is flowing through this, then this is called superficial velocity. Okay. So the superficial velocity is nothing but flow rate of the filtrate divided by the area. Okay. So because this unit is meter per second, what is this V? V is the volume of filtrate. As you can see from this schematic diagram. So filtrate, right? This is the volume of the filtrate per unit time collected. That is the flow rate of the filtrate, right? And what is the area? Area of this filter medium or the cross-sectional area. That will give you the superficial velocity. Okay. Now, you can use other formulas to express this volume of the filtrate and area. So this is equal to this. Okay. So this is nothing but pressure drop applied. What is E? E is the voidage, right? So where is E? Yeah, E, the voidage. Voidage means how much empty spaces are there. Okay. So it is nothing but voidage fraction. So if you have 50% voidage, means 50% of the space is empty. Okay. And what is S? It is a specific surface area of the particle. Suppose you have this solid particle. What is the specific surface area? That is surface area per unit, mass of the solid. What is mu? Viscosity of the filtrate. What is L? L is the thickness of the filter medium or cake thickness. Okay, the L is the cake thickness. Remember what is cake? You have filter medium at the bottom of the cake layer, right? So the thickness of the filter cake is L. Okay, so we're basically focusing on cake filtration. We'll consider the filter medium resistance or its properties later. So first we are focusing on this cake. Yeah. So E is the voidage in this cake. Okay, of the filter cake. How much empty spaces are in the cake so that the liquid can flow through the pores. Okay, so this is the formula. The initial stages in the formation of the cake are therefore of special importance for the following reasons. Because, so this formula is mainly for the filter cake. So if there is a cake filter, so the superficial velocity through this cake, because the fluid is passing through some obstacles, right? Some solid particles. So it is superficial velocity. So this is a function of all these things. right? So it will definitely be depend upon the cake, how cake is formed. So initially there is no cake, right? At t equal to 0. As the time progresses, then the cake is formed layer by layer, right? Over the filter medium. So why it's important? So for any filtration pressure, the rate of flow is greatest at the beginning of the process since the resistance is the same thing I have told you. So for any filtration pressure, if you maintain the constant pressure, the flow rate will be highest or greatest at the beginning of the process because there is no filter cake form at the beginning, right? That's why the resistance is minimum. High rates of filtration may result in plugging of pores of the filter cloth and cause a very high resistance. So if you have very high rates of filtration, if you apply very high pressure, what will happen? The filter cloth pores will be clogged by the solid particles. Okay, then it will offer a very high resistance to flow, or no flow will be obtained. The lastly, the orientation of particle in initial layers may appreciably influence the structure of the whole filter cake. So, so this is your filter medium. Over it, filter cake will form. At initial time, what will one layer will form, then again second layer, right? So, what is the shape of these particles of the first layer of the filter cake? So their orientation, if it is like this, if it is cylindrical shape, if the orientation is like this, or it is horizontal, or at some angle, or any other particular shape, then it will affect the whole, filter cake, right? So now these filter cakes, as you can see, the cake is formed at the top of the filter medium. So these cakes can be divided into two types: incompressible cakes and compressible cakes. As the name suggests, incompressible means you cannot compress. So if this filter cake is formed, you cannot compress it to give this squeezed shape. But if it is compressible cake, then suppose this is your filter thickness of the filter cake form. If you apply pressure, what will happen? If it is gets compressed to different thickness or lower thickness, then it is compressible cake. Okay, so incompressible cakes means you cannot compress it by applying pressure. Okay, so in case of incompressible cake, the resistance to flow of a given volume of cake is not appreciably affected by either pressure difference or cake. So if it is an incompressible cake, the resistance will not vary with time. Okay, it will be constant throughout the process. Okay, but with compressible cake, increase of pressure difference or rate of flow causes the formation of denser cake. So, but if it is a compressible cake, if you increase the pressure, more cakes will be, more solid particles will get deposited and the thickness of the cake will increase over time. Okay, or the denser cake will form, so it will get compressed. Hmm? So this is given like this. So the superficial velocity or this formula, this is nothing but superficial velocity, is given by delta p by r mu l. Why? Because other things, this other part, these are all constant. Right? For incompressible cake. Because if it is incompressible, the voidage, the pores inside the cake will not change with time or with pressure or flow rate. Right? So the voidage will remain constant and specific surface area of particle will be also constant. Okay, so this is for incompressible cake. Okay, so first we will derive for incompressible cake, then we will move on to compressible cakes, how to handle compressible cake. So right now this is for compressible cake and r is a constant. This, it is called resistance. So r is this, is the resistance of the cake. Okay, Okay. So what is the relation between thickness of the cake and the volume of filtrate? So what is the volume of filtrate collected and the thickness L of the cake? What is the relation between? So to obtain, there are some steps you can follow it. Okay, so if you follow it, you'll get this, and volume is this. So volume of filtrate is this. The thickness of the cake is nothing but V by A. Okay, what is this small v? So this is nothing but volume of cake deposited per unit volume of the filtrate. So this small v is nothing but volume of the filtrate, volume of the cake, Vc by V. So volume, what is the volume of the cake and what is the volume of the filtrate? So this is the V. Okay, so you can get it. This is, so what is the volume of the cake? L into A, right? Because L is the thickness of the cake and the surface area of that cake is A. So L into A is the volume of the cake, and what is V? Volume of the filtrate. So you can find out the thickness of the cake like this, and you can rearrange the equation. You will get this V. So if you substitute the value of L, so you can obtain this new equation. So focus on this equation. So dV by dt. So this is rate of flow rate of the filtrate, right? So it is nothing but meter cube per second or liter per second. This is the flow rate of the filtrate. Okay, and A is the cross-sectional area or area of the cake, and this is the pressure difference applied. Okay, why it is minus delta P? Because you are applying high pressure here, and here we have low pressure, right? This is the cake. So what is delta P? Nothing but final minus initial, right? Final is low minus high pressure. So you'll get negative. To make it positive, that's why it's put minus here. R is the resistance by the cake. It is constant for incompressible cake. Mu viscosity of the filtrate. This is what? This is the volume of the cake divided by volume of the filtrate. Right? This is the volume of filtrate. This multiplication will give you the volume of the cake. Okay. So this is the equation for incompressible cake, or we say cake filtration. Okay. Within cake filtration, we have incompressible cake. So this is the equation for incompressible cake in cake filtration. Okay. So with this equation, you can have two modes of filtration. So if you make it constant rate filtration, so constant filtration rate means this dV by dt term is constant. Okay. Or you can make it constant pressure difference. So delta P is constant. Okay. Throughout the step. So for a filtration at constant rate, only pressure will be changing, right? Then V by T is constant. Okay. So if you, for constant rate filtration, you have dV by dt. This is V by T. This is no more dV by dt because this is constant. So we can write V by T. So put this in equation. So you can rearrange it. So this is T, take the reciprocal T by V into V. So if you plot T by V versus V, so on the x-axis if you plot V, on the y-axis you plot T by V, so you can get a linear line like this, straight line. So this slope will give you this value, right? This is nothing but y is equal to mx straight line. That's why it is arranged in this form. Okay. So you can do experiment. Suppose you are with time at 0 time, there is no volume of the filtrate collected 0. After 2 minutes, you have collected some, right? Let's say 0.5 liter and so on. So you can do this experiment and you can predict the cake resistance from this. Okay. And for a constant pressure difference, so this is called constant pressure filtration. So delta P is constant. Okay, you can take this equation. So delta P is constant, and the changing things are what? T by V and V. So you can rearrange this. Okay, so you'll get this. Okay, so you can plot T by V versus V to get a straight line. Okay, so this is T by V and V. So you can get the slope here. Okay, this is for constant pressure filtration. Okay, this here actually you don't have to plot T by V and V. Here you have to plot. So okay, this T by V was constant, right? So you can make it some C. So if you rearrange, you have to rearrange actually. So if you rearrange, you'll get delta P on the left hand side and some constant here, K V. Or you can again rearrange. So you can plot pressure difference versus V. So it will give you y is equal to mx again. So on the x-axis you will V, and here it will be delta P. So you'll get a straight line. Okay? So it will this is actually constant rate filtration because pressure is changing. So this term is constant. But for constant pressure filtration, delta P is constant. So this whole term will be constant. Only thing change will this. Okay. So it has rearranged into this. So you can plot between V square versus T like this, V square on the y-axis and time on the x-axis. Then also you'll get straight line, or you can plot like this, T by V versus V. Then also you'll get straight line. So from the slope you can calculate this term. Okay. Now let's integrate this equation. So if you write in differential terms, this is nothing but, this equation is nothing but dt by V is equal to this term by dV, right? So if you integrate between T1, so let's say after T1 time, V1 volume of filtrate is collected, and to any volume of filtrate or any time T. So if you integrate this equation between these two limits, so you'll get this. Okay, so you can rearrange this equation into this. So if you plot T minus T1 by V minus V1 versus V minus V1, so if you plot like this, so on the x-axis you have V minus V1, on the y-axis you have minus T1 by V minus V1. Okay, so you'll get something like this. So slope will be equal to this. What will be the intercept? So this will be intercept. So intercept value will be this. From these two slope and this, if you from the graph you can get the slope value, right? From this you can get the intercept. So if you put these values, you can calculate all other factors. Okay, what will be the pressure, or what will be the pressure will be given, so you can find out other membrane cake resistance and so on. Okay.